Welcome back, everyone, to the Deep Dive. Today we're going to be tackling something really fascinating,
Mm-hmm.
algorithms,
Yeah.
which sound kind of intimidating,
Right.
but are really just those like step-by-step procedures
Yes.
behind pretty much all the technology we use every day,
Yeah.
from, the apps on our phones
Uh,
to like the biggest complex computer systems out there.
Exactly.
And for this deep dive, you sent over this awesome YouTube series that really gets into the nitty-gritty of how algorithms are developed.
That's right.
So we're going to be exploring a whole bunch of stuff today. We're
Yeah.
going to be comparing different algorithms that are
Hmm.
actually designed to achieve the same goal.
Uh-huh.
We'll look at how you actually go about designing an algorithm from scratch
Yeah.
using both flowcharts, which are like those visual diagrams,
Mm.
and also just plain English, or what's called pseudocode.
Exactly.
And then we're going to get into some really cool strategies for taking an algorithm that you already have
Right.
and tweaking it
Yeah.
to solve a totally new problem.
Yeah. Adapting it to a new purpose.
So basically, our mission today is to sort of demystify algorithms.
Yeah.
We're going to highlight some of the potential pitfalls that you might not see coming.
Exactly.
We'll appreciate the cleverness that goes into designing them in the first place,
Mm-hmm.
and really emphasize why being super careful with the design and testing is absolutely critical.
It's so important. Yeah.
The goal is for everyone listening to come away with a much clearer understanding
Yeah.
of these really foundational building blocks of computation.
So fundamental.
Yeah. So let's jump right in.
So let's get started.
I think the first thing we looked at in this series was comparing different algorithms.
Yes. That was the first sort of topic that we explored, and it's such a crucial place to start, I think.
Right.
Because often when you're trying to solve a problem with code,
Yeah.
there's not just one right way to do it.
Uh-huh.
You might have several different algorithms that could
Yeah.
all potentially produce that same end result.
Uh-huh.
But as we saw in this material, sometimes even tiny differences
All right.
in the structure of an algorithm
Yeah.
can lead to some really surprising and different outcomes.
Yeah, like I was surprised by that temperature check example.
Oh,
Remember that?
that was a good one.
We had two algorithms that
Yeah.
were essentially designed to display a message based on the temperature outside.
Uh-huh.
They were both using Boolean expressions to check if the temperature was above 90 degrees or
Oh.
above 65 degrees.
Yeah.
And a Boolean expression, if you're not familiar,
Uh-huh.
is basically just a statement that's either true or false.
Right.
It's like the temperature's over 90 degrees.
Yeah,
That would be a Boolean expression.
exactly.
The thing is, the first algorithm in the example, it like nested these checks.
Yeah.
So one check was performed inside the other,
Right.
whereas the second algorithm laid them out sequentially,
Yes, one after the other.
one after the other.
Uh-huh.
And it was so interesting to see how that one little structural difference
Yeah.
played out when we actually ran the algorithms
Yeah.
with different temperatures.
It was so surprising.
So when the temperature was 54 degrees,
Yeah.
they both correctly decided it's too cold outside.
Right.
So far, so good.
Yeah, they agreed.
But then when it got really hot, like 95 degrees,
Yes.
the nested algorithm did what you would expect.
Right.
It was like, it's too hot outside,
Yes.
and then it stopped there.
Right.
But the sequential algorithm,
Yeah.
it also said, it's too hot outside.
Uh-huh.
But then because it kept going and evaluated the next condition, which
Yeah.
was, is it greater than 65 degrees?
Uh-huh.
It also displayed, sure, I will play outside.
Oh, it did both.
Which was like,
It was contradictory.
that doesn't make any sense.
Right. Like you wouldn't want to play outside if it was that hot.
No way.
No.
So even though the logic seemed similar on the surface,
Right. Superficially, they seem similar.
yeah, that sequential evaluation
Yeah.
just totally messed things up.
It created this nonsensical result.
Yeah, so it's like a hidden mug.
Right. Exactly.
Yeah.
Yeah. It highlights how important it is to really carefully analyze
Yeah.
your algorithms.
Yeah.
Because you might look at two algorithms and think, oh, they're basically the same.
Yeah.
But even these little structural tweaks
Right.
can have these huge unintended consequences
Totally.
on what you actually get as the result.
It's not just about finding these differences, though.
No.
It's also about understanding how to make the algorithms equivalent
Right.
when you actually want them to produce the same result.
Exactly.
So the example showed how you could adjust that second algorithm,
Yeah.
the sequential one,
Huh.
to make it work more like the first one
Right.
by adding an and condition,
Yes.
specifically checking if the temperature was also less than 90 degrees
Uh-huh.
before it suggests going out to play.
Right. So it had to be both above 65 and less than 90.
Yeah, and that little addition of and temperature less than 90 basically made it mirror the logic of that nested structure.
Exactly.
And that to me was like the really cool part.
Yeah.
It shows that you can actually express the same logical idea in different ways.
Right, and they'll both work. It's just a matter of which
Yeah.
one is maybe more appropriate
Yeah.
for the situation.
And then the source material went on to like an even more abstract example.
Yes, it did.
It was looking at this nested if-else structure
Right.
that was assigning a Boolean value to a variable called drive work
Mm-hmm.
based on two conditions,
Right.
whether it was a holiday and whether it was a weekday.
Exactly.
And the takeaway there was that this whole nested conditional structure,
Yeah.
which is basically checking one condition and then another based on the outcome,
Right.
could actually be replaced by a single Boolean expression.
That's pretty neat how they showed that.
Yeah, it was cool. They used a truth table
Yeah.
to show all the possible combinations
Sure.
of true and false
Sure.
for the inputs and the outputs.
Exactly. And it demonstrates how both the conditional structure
Yeah.
and that Boolean expression, which was, is holiday ND is weekday? Or not, is holiday ND is weekday?
Yeah.
They produce the same exact true or false outcomes.
Yeah, it's pretty mind-bending when you first see it.
Yeah, it is.
Like how these different forms of logic can be interchangeable.
Right, because when you think about them individually,
Yeah.
the nested if-else and the Boolean expression,
Uh-huh.
they seem so different.
Yeah.
But ultimately, they're achieving the same thing.
Yeah, and I was wondering, like, practically speaking,
Yeah.
when would you actually choose
Hmm.
that more complex Boolean expression over, like, the nested if-else,
That's a great question.
which is easier to understand?
Yeah, it's a question of clarity versus efficiency sometimes.
Yeah.
Because both of them achieve the same logical outcome.
Right.
But sometimes that single Boolean expression can actually be evaluated a tiny bit faster by the computer
Okay.
than a bunch of nested checks. So if you're in a situation where like performance is really critical,
Mm-hmm.
you might want to go with that Boolean expression even if it's a little harder for a human to read.
Okay, so it's like a trade-off.
Right. It's about having the tools and the flexibility to choose the right approach for the specific problem you're solving.
Yeah, that makes sense.
Yeah.
So we've talked about comparing and even making different algorithms equivalent.
Right.
Now let's get into actually developing them from scratch.
Yeah, that's where it gets really fun.
Yeah, the source material talked about flowcharts and natural language.
Yeah, those are two fundamental methods for designing algorithms.
Okay, so flowcharts are like visual diagrams.
Yeah, exactly. They use symbols and arrows
Ah.
to represent the steps and the decisions in an algorithm.
Okay.
And then natural language is just describing the process in plain English.
Right. Or pseudocode.
Or pseudocode, which
Ooh.
is like a simplified version of English
Yeah.
that's specifically meant to outline the logic
Ah.
before you actually write the code in a specific programming language.
Okay, cool.
Yeah.
And the robot navigation example was perfect for this.
Oh, yeah, I love that one.
You've got a robot on a grid
Uh-huh.
trying to get to a gray square.
Right.
The first approach they took was just like listing out every single action.
Yeah, just a sequence of steps.
Like move forward, rotate, right.
Right.
Move forward, rotate left,
Uh-huh.
and so on.
And you can quickly see how that would become a problem.
Yeah.
Because if the path is complicated at all, that list of instructions is just going to get
Yeah.
so long and tedious.
And probably really error prone.
Exactly. And it's not very efficient or elegant.
No.
It's just not a good way to program a robot.
So that's where iteration or looping comes in.
Yes, looping is a lifesaver.
Instead of writing out that whole sequence over and over,
Right.
you can use a repeat until structure.
Yeah, like repeat until goal is reached.
Exactly. And that makes it way more manageable.
It's so much more concise and easier to understand.
And the pseudocode example showed that.
Right. It clearly showed that block of actions. Yeah.
Being repeated within the loop.
Yeah.
It was really helpful.
We also looked at like a real world example of calculating the cost of an item
Oh, yeah, that was a good one.
where there might be discounts
Uh-huh.
and then sales tax on top of that. And this
Okay.
is where selection or conditional statements come in.
Yes, that's the if this then that logic.
Right.
So you've got these different rules,
Yeah.
like a 25% discount if it has a green tag,
Uh-huh.
60% discount if it's a red tag,
Right.
and then you add sales tax after the discount.
Yeah. So the algorithm has to choose which discount to apply.
Yeah, it has to select the right one.
And the pseudocode for that was really clear.
It showed those different branches
Yeah.
based on the tag color. It was easy to follow.
And then the final example was that game scoring algorithm
Yeah.
where you get 4 tries to roll a random number.
Uh-huh. Between 1 and 10?
And your score is the highest number you get.
Right.
That one was cool because it combined iteration.
So repeating the roll 4 times with selection,
Right.
because you have to decide if you need to update the score.
Yeah, does the new roll beat the old high score?
Exactly. And they had all these variables to keep track of the number of attempts,
Right.
the current score,
Uh-huh.
and the temporary score from each roll.
Yeah, it was all very well organized.
So basically what we're seeing is that algorithms aren't just a straight line of steps.
No, they're usually a combination of different control structures,
Yeah.
like sequence selection and iteration.
And the way you order them,
Yes.
even nest them inside each other.
Exactly.
That's super important.
Yeah, it's what defines the logic of the algorithm.
Right, and determines how it actually solves the problem.
Exactly.
So now let's move on to modifying existing algorithms.
Yeah, that's a really practical aspect of working with algorithms.
Yeah, because you don't always have to start from scratch.
Right, it's often much more efficient to build on something that already exists.
Yeah, the example they gave was the Collatz conjecture.
Oh, yeah.
Have you heard of that?
Yeah, I have. It's a famous unsolved problem in mathematics.
Yeah, basically you start with any positive whole number,
Uh-huh.
and then you apply this rule over and over.
Yeah, if it's even, you divide it by 2.
Huh.
If it's odd, you multiply by 3 and add 1.
And the idea is that no matter what number you start with, you'll always eventually reach 1.
Yeah, they think so, but no one's been able to prove it yet.
So they showed how you could take an algorithm
Yeah.
that already existed
Uh-huh.
for figuring out if a number is even or odd
Right.
and modify it to do the Collatz sequence.
Yeah.
So they replaced the original display actions with the Collatz operations.
The dividing by 2 or the multiplying and adding 1?
Exactly. And then they put that whole thing inside a loop.
Yes, repeat until the number equals 1.
And then they added a step to display the number at each step.
Yes, you can see the whole sequence unfold.
And I thought that was so clever
It is a really smart approach.
because you're building on something that you know already works.
Right.
So it saves time
Yeah.
and it reduces the chance of errors.
Uh-huh.
You're basically leveraging existing code.
Exactly. It's all about modularity and building on solid foundations.
Yeah, that makes a lot of sense.
Yeah.
Then we had that robot navigation example
Yeah.
where they had an algorithm to move the robot to the gray square.
Uh-huh.
And it worked perfectly at first,
Yeah.
but then they changed the grid a tiny bit.
They did. They just removed one black square.
And that messed everything up.
It did. It broke the
The
algorithm.
robot got stuck in a loop.
Yeah, it was just repeating the same moves over and over.
And that just shows how even a little change
Right.
can have a huge impact.
Yeah, it can totally change the behavior of the algorithm.
So they had to modify it.
Yeah, they added a check to see if the robot could move left
Right.
before checking if it could move forward.
And if it could move left, it would do that first.
Exactly.
But even that wasn't perfect.
No, it wasn't.
They found another potential problem.
Yeah, where the robot could get stuck if it couldn't move left, forward, or right.
And that's what I love about this whole process.
Yeah.
It's like this iterative cycle of modifying, testing, and refining.
It's how you make sure your algorithms are really robust.
So the final fix was to just always turn right as a last resort.
Yeah.
If it couldn't move left or forward.
Exactly.
And this whole thing really emphasizes the importance of thorough testing.
Yes, testing is crucial.
With lots of different scenarios.
Absolutely.
You have to make sure your algorithm works no matter what.
Right, you have to test it under all sorts of conditions.
And the source material made this really important distinction
Uh-huh.
between modifying an algorithm
Yeah.
and just copying it.
Right.
Modifying means you're actually changing it to meet new requirements.
Yeah, you're understanding the underlying logic and adapting it.
Right. You're not just blindly copying and pasting.
Exactly.
So to sum up our deep dive today, we've seen that you can implement algorithms in different ways, but those structural differences can have a big impact on the results.
Right.
We've learned about control structures like iteration and selection,
Yeah, those are key for solving complex problems.
and we've seen how you can modify existing algorithms,
Uh,
but you have to test them thoroughly
yes, testing is so important.
to make sure they work in all kinds of situations.
Exactly.
So all of this is about understanding how algorithms work,
Yeah.
how to design them, compare them, and change them.
Uh-huh.
And it really gives you a new perspective
It does.
on the technology we use every day.
It helps you appreciate the logic behind it all.
Yeah. Okay, so here's something to think about.
Okay.
Think about something you do regularly,
Mm-hmm.
like making coffee or planning your commute.
Okay.
Could you break that down into a step-by-step algorithm?
That's a good question.
And if you did, what variations or edge cases
Right.
would you need to account for
Uh-huh.
to make sure it always works perfectly? I like that. It's interesting to think about how much algorithmic thinking
Yeah,
we already do without even realizing it.
absolutely.
Thanks for joining us for the deep dive.
It was fun.
See you next time.
See ya.